Hi everyone, hope you're fine and doing well in these very extraordinary days. Let's carry on with our lectures about operating system. In the previous lecture, I introduced the operating system and I mentioned how it works. Operating system, as I said, is a big program that acts between the user, the system service interface, and also the hardware. And using the operating system, a user can have access to the hardware and execute his program. So this operating system, and it's got different modules. One of the most important modules that we have in operating system is process manager. But what is process? And I'm going to discuss process and process managers in this lecture. Let's start. What is process? I'm sure that you have seen this Windows Task Manager, and whenever you have a problem, you see that your computer is freezed. The first thing that you want to check is the Task Manager. If you actually open this window, you see different software or processes here that are working, and probably one of them has got a problem. So, what is process? Process is the unit of work in a computer system. When you run a program, at the same time, you run multiple programs. Each of them are the processes that are executed by the CPU. So in the Windows machine, you can see the process like that. And in Linux machines, by using these two syntaxes, you can see the list of processes that exist and are working. So this is one definition of the process, is the unit of work in the computer. But another one, which is actually a bit more abstract, but I think it's quite good. It says that process is a sequence of states resulting from the action of set of instructions on the states as they develop. So what it means is that process is different situation that happens in running a program. For example, in the fetch exit cycle, the famous example for adding or subtracting two numbers, in each step, the computer, the registers, should load and save some data, step by step, passing to different registers, save them, load them, and so on. Each step is called a state. So a sequence of these states, which actually runs by instruction, we call them a process. So process is the unit of work which actually contains all of these steps for running a program. But how computer and how operating system manage these processes? As you see here, and similar to what we have in networks and packets, we've got a unit of data or data structure for that. So operating system manages this process using this block of information for each process, which is called a process control block. So operating system, to manage the processes, maintains a data structure known as a process control block for each process, and it contains loads of information that we're going to discuss in more details. This enables operating system to manage different processes effectively by saving the current state there and loading them. So we use this block to save and load the data for each process. So what's that? Let's go into more details. Each process has got two parts. One of them is a static part, or it's called task. What is task? Task is the resources allocated to the process, which includes the amount of memory that it needs, where it's coming from, the directory, the sources, input, output, such as keyboard, screen, and so on, connection with other network, with other process, with other jobs, other programs, and also something which is important, which is a static, it's not dynamic, is a program. Program on its own is bunch of lines. So it's sequence of instruction, but as long as you don't execute them, you don't actually run them, it's static. So all of this information goes to the static part of your process, which is called task or resources. Not only that, we've got dynamic part. As you see, that's a good sign for the dynamic part. Dynamic part is the part of the process that run the program, execute the program. Instructions that make up a program are actually being carried out. And what is called? It's known as thread of execution, thread of control, or simply thread. So this thread has access to all the information for this process here and run the program. A standard process actually has got only one thread, but we've got different type of them that I will explain. But definitely, it's got resources there. So maybe it doesn't make sense, and I thought a better example for that. I found a really good example, which is comparing the operating system with baking a cake. The process, which is unit of job here, is making a cake, because we want to make a cake is exactly the same as job that we want to do in operating system, is a process. What are the tasks? The resources, the ingredients. In baking a cake, ingredients are our resources. Program is our recipe. Recipe on its own is a static thing. We cannot run it. We can read through the recipe and do the stuff. So thread is the actual sequence of operations carried out. For example, for baking a cake, mixing, baking, and all of them are thread, or the actions that a process does. So I hope that by this example, you understand what is task, what is thread, and what is process. Let's move on. I explained that before this, but let's see the relationship between the process and the process. So obviously, a process is the agent which runs a process by executing the instruction contained in the associated program. So processor execute the process which contains the instruction. For sure, in even very fast machines and supercomputers even, we've got fewer processors than processes. So we have less processor than processes. Because of this, processes get their share of time on the processor. It means that each process has got a certain amount of time that can use the processor. So that's quite important. And also, those processes actually which are not in waiting can use the process, and processor actually is not offered to those processes which are in the waiting. So for example, if a process is waiting, for example, for pressing a button, it cannot use the processor. It's got to wait until you press the button. Let me give an example. Imagine that we have two processes, process A, process B. This is one in software, this is the other software. And their data, their instructions, and so on, and they need some data on the memory. For example, disk drive 1 and 2. So process A executes. Process A execute. This shows the, as you see here, solid line represents CPU execution, and the dashed line represent operation of a disk drive. So what happens? You execute the first one. The process A executes. When it gets to this point, it needs some data. It requests some data from the disk drive. So what happens? The operation is happening here to deliver the data to the process A. At this point, it's got to stop, save its state, whatever it is, and CPU is idle. What we don't want that happen. What happens? Process B starts happening. Process B executes. At this point, when it finishes this bit, it needs a data. Again, it's got to go back to the disk and read the information. So still, we need to wait to our data to be delivered from disk drive 1. This process B finished, it needs data. At this point, as you see, the CPU is idle. It's not working. As soon as the data is delivered, here, the process A starts running again. But at this time, it's got to, when it stops, it's got to save the state. When it wants to rerun again, it's got to reload that. As you see here, there shouldn't be any overlap between process because we've got only one processor at this point. But doesn't matter if there is an overlap between them. At the end of that, process A actually can work, or process B, or whatever. So as you see, we've got a gap here. The CPU is idle. Another problem is that We've got to save here and rerun again. Save the state, load the state. Same story for that. That's a problem. Let's see what this problem is. Overhead. It happens frequently that a process begins running on a processor and almost immediately stops again to wait for some input to become available. Here, it stops and it wants to run again. In this time, it's got to save the data and reload the data. The operating system has to save or restore the whole state of the machines as it was at the moment when the process stopped running or begins running again. This saving and loading the data again between each part of the process which is being executed is an overhead. And imagine when you are more processes, the story becomes more complicated. The number of the process increases, and it would be a very complex situation, and computer cannot handle that easily. What is the solution for that? One of the possible solutions that we can have for this problem, for the overhead, is to have multi-threading. What is multi-threading? In multi-threading, I will give an example again based on that famous example that I said for baking a cake. But at the moment, instead of having only one thread, as you see here, we can have multiple threads. What happens is that we try to break down the processes, break down the threads, the executions. So for example, if this one is running, if it blocks, if something happens to that, within the same process, something else happens in terms of the program. So if one thread is blocked, another can execute. So for stopping and running again, because that happens within the process, we don't need to save the whole and entire data again into the process data block. What happens is that it's not necessary to save and restore the full state of the machine for this, full state of the whole thing. Each of them, it's just jumping to another location in the program code because they're running the set of instructions. So instead of running from all of them by this thread, that can be done by multiple threads. So what happens? Each thread must maintain some state information on its own. So it's got to only save this amount of information, not to save the whole thing. As you see, by using the multi-threading, we reduce the load of the machine massively. Because instead of saving and loading the whole state, we only save and load the little bit of data which relates to this thread. Let me give an example. For example, we want to listen to music, watch a video, whatever, on VLC player. If you have one thread process, we've got to have one process for loading, for opening the VLC, one process for loading the music, one process for playing. But if you have, for example, 3 threads, one thread will go and open the VLC. The other one goes and bring more music. The other one actually play them. So as you see here, they shouldn't wait for the other one to run. When you're listening to one of them, the other one can go and bring more music to the VLC player. So by multi-threading, as you see, the efficiency of a machine increases massively. So multi-threading enables the processing of the multiple threads at one time rather than multiple processes. And as I said, it's quite important for the scalability and efficiency of our machines. Example. Baking a cake, I explained that. Let's go to the next step, which is baking several cakes. Bigger problem. The task, which is the resources, are the same. Program is our recipe. Process is making several cakes, but thread is different. If you want to use one thread, we've got to wait till end of baking a cake, which is actually putting the material into the oven, and wait for that to be baked and take it out and actually again do everything in terms of the operations, mixing and so on. But while one cake is in the oven, we may be mixing the ingredients of the other one. We shouldn't wait. Immediately when we finish the first one, put in the oven, we can start making the next one. This one, which as you see, increase the efficiency of baking several cakes, is multi-threading. We use multiple threads for that. So in the example that I said, process A waits here, get data, and run again. As you see, save, load here. But if you have again the same process, this is the first same process, and even we've got data on different places, first we have 3 threads for that. So the first one is done, then we finish, goes to this one, finish, goes to this one. As you see, there is no idle time for the CPU, and they can run one after each other without saving the whole data, without having an overhead for the operating system to go save, load, save, load. No, that happens within the threads. We've got 2 types of threads. One of them is user thread. As you remember, I explained this graph in the previous lecture. User thread is for user mode, that most of the things are happen in the applications. And the programmer, they are quite good. They can write multiple threads and different threads in their programs. So when they run the program, the operating system actually doesn't do this switching between the threads. The programmer has actually have done that, and this saves on the overhead of the button in the operating system each time control changes from one thread to other one. The operating system gives control of the CPU to a process. The other one, which is these days we use that in most of the modern operating system, is kernel threads. That kernel does the job. Operating system handles all the switching between the threads. All modern operating system actually does that, and allowing the kernel to perform multiple simultaneous tasks to services multiple kernel system called simultaneously. So everything, it happens in operating system, and it becomes very, very faster. So I stop here and go back to that in the part 2 of this video.